Hey there, welcome back to 2241. This is the 2.1 examples video, and here we'll be talking about vector functions and parametrizations, working through some exercises. All right, so let's get started with number one. Just to zoom in a little here, maybe it's kind of small, sorry. We need to identify the component functions of this vector function and compute the domain of R. Okay, so let's see how this works. The component functions are pretty straightforward. It's just look at the vector itself and say, what's the x, y, and z? These can be different, by the way, depending on what basis you're using, but that's the question for linear algebra. Just wanted to make sure that that is at least out there. So let's write down our component functions. And sometimes these are better written as x of t equals t cubed, y of t equals log 3 minus t, and then what was z? It was the square root of t. Okay, so those are our component functions. Now let's finish off the question and say, what is its domain? So the domain, I'm going to write out a formal thing here. So the domain of the vector function R is equal to the domain of the function x intersected with the domain of the function y intersected with the domain of the function z. So it is all values of t which make all of these, or for which all of these functions are defined. So all t values where all of x, y, and z exist. Okay, and so we can go ahead and compute the domain of x. So that one is pretty straightforward. The domain of x is, well, it's a polynomial here, so its domain is all real numbers, which sometimes we write as negative infinity up to positive infinity. All right, next we have the domain of y that we need. Well, okay, we have the log function, and we know that the log, the domain of the log function is 0 to infinity. So whatever gets plugged in here needs to be a positive number. So we need 3 minus t to be positive. So the domain here is all t values, set of all t in R, so that 3 minus t is greater than 0. Or set of all values t, so that t is less than 3. All right, we can write that as an interval. That's going to be minus infinity up to positive 3. And then the open bracket means not including 3. All right, last we have the domain of z. And this is the square root function, which we know exists for all positive real numbers, sometimes also written as R plus. Okay, and then using these, we can compute our domain of the vector function. It's just going to be the intersection of all three of them. So let's bring this down here. And we'll say that this is, actually, you know what? Let's put that here. and then we will finish down below. So we have negative infinity to infinity intersect with negative infinity up to positive 3, intersect with 0 up to positive infinity. And we're looking for the set of all values, which are common to all three of these sets. Okay, well, this set includes everything, so we can more or less just drop it. It doesn't help us decide anything. This set includes all numbers between that satisfy t less than 3, and this set satisfies all numbers t greater than 0. So we need to satisfy the inequality 0 less than t less than 3, which means that we have our interval from 0 up to positive 3 as the domain of vector r. And that's it. That's how you compute the domains of vector functions. Okay, so let's move on to problem number 2 here. Here we have a limit that we want to compute. Yeah, okay. So let's go ahead and compute this limit, see how this works. So if we use the definition, we'll remember that the limit of a vector function is just the limit of all three of its components whenever these exist. So we need the limit as t goes to 0 of 1 plus t cubed. All right, that one's pretty easy. It's just 1 because t cubed at 0 is 0, and these are continuous. The limit as t goes to 0 of t times e to the minus t. Well, e to the 0 is 1, and 0 times 1 is 0. And then the limit as t goes to 0 of sine of t over t. Well, we learned in freshman calculus that this is 1. So the limit of the vector function r as t goes to 0 is the vector 1, 0, 1. All right, pretty straightforward. All right, now we're going to start talking about some space curves. So describe and identify the space curve given by the function this. So we have 1 plus t, 2 plus 5t, and then negative 1 plus 6t. Okay, well, if we remember from our, so the last section, the lines and planes section, we have parametric equations here. 1 plus t, 2 plus 5t, and negative 1 plus 6t. Another thing that we can do is we can use some vector algebra here, and we can rewrite r as, okay, 1, 2 minus 1 plus 1, 5, 6, and then times t. And now we can see that this is of the form r0 plus v times t. And this is just the vector equation of a line right here. So this is a line in R3, and we can describe it using these vectors. It starts at, or it contains the point 1, 2, minus 1 maybe, and moves in the direction of v, 1, 5, 6. So not so much in the x, but pretty steep in the y and z directions. All right, and that is our line. Last, we want to, I'm going to move this up a little bit, give us some more space. Last, we want to sketch the space curve that is the image of this vector function down here. Okay, so we have r of t equals cosine t, sine t, and then t for the k hat component. All right, well, let's write down our parametric equations. And maybe we'll understand some stuff a little better. Z of t equals t. Okay, so if we look here at the x and y, we'll ignore the z for a second, we notice that these are trigonometric functions. And in fact, these are exactly the functions on the unit circle. So if I plug a value of t into this, it's like plugging an angle in to the unit circle and getting out some x and y coordinates. So different values of t trace out a circle in the xy plane using these functions for x and y. All right, so we know that the projection of this curve in the xy plane then looks like this. So unit circle and in the xy plane. And let's see how let's think about how this is traced out. It's in the standard parametrization. So t equals 0 gives us a point over here, and then we trace this out in this direction. Okay, so you get pi over 2 and pi over 3, or sorry, yeah, pi over 2 and pi, and then 3 pi over 2, and then back to 2 pi. And then we'd keep going around the circle like that. Okay, but we have three functions here. We have x, y, and z. So this is a three-dimensional space curve. And what's happening is that as we go around this circle in the xy plane, in the z direction out here, we're actually sort of lifting off the plane all the time. So whatever plane we're currently on, we're lifting off of it. We're moving along the z direction. And that is how we get a helix. And that's what this curve is. So this is a helix along the z direction. All right, so let's go ahead and make our xyz coordinate system. And actually move this down a little bit. And put z way out there. X, Y, and sort of freehand this. If I draw my helix, it should do something like this. Go around, and then come back up, and go back around, and come back up, and so on. And so we have a helix along the z direction. And if you look at negative values of t, this guy is also going, or is also coming from down here. So your helix extends infinitely in the positive and negative z directions. All right, so that's the space curve. This is sort of a classic example of a curve traced out by a vector function. All right, next page, we've got some more examples here. All right, find a vector function whose corresponding space curve is the line joining these 2 points. Okay, well, we've actually already done this, again, in the lines and planes section. So if you remember, we have the various forms of a line in 3D space. One of them is particularly easy. You could get a v vector by subtracting these two and then writing out, okay, p plus that v vector times t. There's an even easier way if you remember the convex form of a line. So it's the convex combination of these 2 points. What is a convex combination? Well, it's this. So 1 minus t times p as a vector plus t times 2 or times q as a vector. Okay, so if we write this out, we get 1 minus t times 1, 3 minus 2 plus t times 2 minus 1, 3. All right, and now we can go ahead and combine these things if we want to, and we can get the standard vector form of a line. So if we distribute this vector to the 1, we get 1, 3 minus 2 as our sort of base starting point. And then plus, well, what vector do we get for the t components here? So we have minus, so we negate all of these or subtract them from all of these. So 2 minus 1 is 1, and then -1 minus 3 is -4, and then 3 minus -2 is 5, and that was all times t. And so we have both forms of our straight line in 2D space. And also note that this is for t from 0 to 1. So this would be the line segment from P to Q. If you were to extend t further, then you would get the entire line. All right, problem 6. Find a vector function whose space curve is the intersection of the surfaces x squared plus y squared equals 1 and y plus z equals 2. Okay, so this is one of those tougher objectives, and I'll show you how to think about this. I like to draw pictures of these first. I think it helps a little bit. It does also help to know what these curves are based on their equations. Actually, surfaces, not curves. So we've got x squared plus y squared equals 1, and hopefully you'll remember that that is a circular cylinder, right circular cylinder, along the z-axis. So we have a cylinder that looks something like this. And put the bottom on there. Okay. So there's our right circular cylinder. X squared plus y squared equals 1. And then we have the plane y plus z equals 2. Okay, well, if we think of this as an equation in just the yz plane, well, I know it's a straight line, and I know that maybe from our lines and plane section, this is going to be a plane. But there are a couple ways to go about this. One of them is just to think of this as a straight line in the yz plane. And that is going to be, right, z equal 2 minus y. So slope of -1 that passes through z equals 2. And maybe let's do this one let's do this one in blue as well. And so we're going to have something that does like that. I think that's about right, about what we're looking for. Okay, so that should be our intersection of this plane with the YZ plane. And we extend it along the x-axis, our plane should look something like this. And it's gonna slice our cylinder in a specific way. In an ellipse. Move that a little bit there. These are kind of tricky to draw. Oh, no, wait, look. Come on. Okay, good enough. So we have a plane that slices our cylinder in an ellipse right here. Okay, so we need a vector function that parametrizes the ellipse. Real quick, another way that you could have found that plane is by remembering that y plus z equal 2 can be thought of as the expansion of the vector form of a plane. So we have 0x plus 1y plus 1z equals 2. And so we then have a normal vector of 0, 1, 1. Where is 0, 1, 1 in this plane? Well, 0 in the x direction is where we move. And we point 1 in the y and 1 in the z, which is going to be normal to this plane that we can see. All right, so this also works to get a normal, or to get the plane. Okay, so now we need to parametrize this guy. It's helpful to notice that cylinders have standard parametrizations. So we have x of t equal cosine of t. And if this was like x squared plus y squared equals 3, then we'd write square root of 3 in front of that cosine. Now we have y of t equals sine of t. We don't need to have it this way, by the way. We can also swap these and get a valid parametrization. It just gives us things being traced out in a different direction. Okay, and then now how do we get z from this in order to make an ellipse? We use our other equation. So the parametrization for the cylinder here is just these x and y values, and then z is whatever it wants to be. We also have the plane which intersects and then restricts our allowed values based on this equation. So we have z equals 2 minus y, which is the sine of t. Sine of t. And so there's our parametric form, and we want a vector function, so we just need to rewrite it in vector form. As r of t equals cosine, sine, and then 2 minus the sine of t. And there we go. There's our vector function at the intersection of these two space curves, or space surfaces. All right, so that is 6 out of 13 exercises, I think. And the next ones are a little bit trickier. So I'm going to stop here and start a new video for the rest of these examples.